In the previous lectures, we learned about two data structures, an array and a linked list, and we used these two data structures to implement stack and queue abstract data types. Today, we will see how we can use the same data structures to implement another abstraction called a list. Imagine that you maintain a dataset of world records, where you record the best athletic achievements for some sport. You want to be able to perform the following tasks on this dataset. First of all, you want it to be dynamic. You should be able to insert a record at a given position or remove the record from a given position. Because the athletes work hard and their ranking positions can change, and new athletes constantly compete for their position at the top. Also, you want to be able at any time answer the following queries. Who is the second fastest athlete in the world? Or, for example, what is the current world rank of Hikaru Nakamura? We are dealing here with a collection where the position of each element inside the collection is important, and we also need operations to access the item at a given position. Note that it is very different from what we were doing before. Before, we also only needed an access at the end of the sequence. For both types of queues that we learned, stack and queue, we needed to access the sequence only at the end. Now we also want to be able to access the sequence in the middle at a given position. We model this sequence where the order is important. We model it using the abstract data type called list. And we require this data type to support the following operations. Get item by position. Find the index of an item inside the sequence. Insert a new element at position j, or remove an element from a given position j. Note again that at this point it is just an idea, our desire, our dream, but now we will discuss how to bring this idea to life. We can implement the list idea using an array data structure. We need to maintain the size and capacity as before, and we will not limit the capacity, but make an array dynamic. We will double its capacity each time it is full. We can also implement the list idea using a linked list data structure. In this case, we need to store the reference to the first node in sequence, and everything else will be recoverable by traversing a sequence of links. Next, next, next. Let's look at what efficiency did we get for all these operations with these two implementations. If we implement the list ADT using an array, then on the positive end is that we can get an element by position in a constant time, and removing adding to the end of this array is mostly very cheap and also can be done in a constant time. negative performance we get when we adding and removing from position 0. In this case, we would shift big O of n elements of the array to the right. Adding to the end can also slow down because sometimes the array will be full and we would need to double its capacity. We also can end up with a wasted space because it's a very dynamic data structure. So after we double an array, we create a large capacity, large space occupied, but after we delete a lot of elements of the array, we might end up with many empty slots. The problem is that dynamic arrays sometimes grow, but they actually never shrink back. If we implement the list ADT using linked list, all we need to know is the reference to the head of the list, stored in a variable head, and we also can optionally store the number of total elements in the sequence in a variable size. Okay, so what performance do we get with the linked list implementation? First of all, we do not need to worry anymore about running out of space. There is no need for doubling, and the list can grow as much as there is available memory in the computer. There are never empty slots, and we have a direct access to the head in constant time. That means we can remove or add elements in the beginning of the sequence in a constant time. On the other hand, we have space overhead to keep links. Those are reference variables in each node. So together with each piece of information in the sequence, we also have a reference variable for the link. There is a difficulty to access letter elements. It still will take big O of n because we must always start from the head and traverse forward. So the efficiency of getting an element by position available with array implementation is gone. Let's discuss some possible improvements to the linked list data structure, which can help us to improve efficiency of some operations. First of all, we can make good use of a tail pointer. With a tail, adding at the end is fast. Removing from the end does not improve. We know that we do not have an access to the node before the last, and we cannot reset the tail in case of removing the last node. The next improvement idea is to add links backwards. In each node data structure, we are going to have a link to the next node in sequence, but also another link to the previous node in sequence. Originally, both these reference variables are set to null, and then we will put into them the corresponding references to other nodes. Here is a visualization of a doubly linked list. We have just two pointers, to the head and to the tail of the list. But each node now contains the link to its predecessor and to its successor in sequence. We can traverse the list in both directions, starting either from the head or from the tail. With such an amazing data structure, we might ask ourselves, why do not we always use the doubly linked list? Why would anyone settle for a singly linked list? This is because in situations where we do not need backward traversal, we can use a singly linked list to save space on previous field for each node. And also, for some tasks such as implementing stack and queue, we do not actually need an efficient removal from the end. We never remove from the end for these queues. With a doubly linked list, all operations are also much harder to be implemented. We need to reset not only the next, but also the previous of each node involved in the modification. As an example, consider adding a new node in the beginning of the doubly linked list. In a singly linked list, if the head is not null, then we accomplish this in just two operations. New node next equals head and reset head to new node. This relatively simple addition for a singly linked list now becomes more complicated. So the first thing we do, new node next is equal head. Now we need to update the previous of the head to point to the new node. And finally, we reset head to point to the newly added node. Note again that the order of these operations is very important. And that is only for the comparatively simple case of adding in front. Let's try the removal of a node in a doubly linked list. Note again that we just need to reset all the pointers, not only the forward pointers, but also pointers to the previous node. So getNode here is the method which returns the node at position j of the linked list. Try it out. Which of the following is correct? Which of the following correctly remove the node at position 1? Stop the video and try it with the top hat quiz. This question is called Remove at position I in doubly linked list. In summary, with doubly linked lists, we have links in both directions. We can traverse forwards and backwards. All tail operations now are run in time big O of 1, because we have direct access to the tail node and also to its predecessor via the previous link from the tail. As a negative, we see that there is an additional code complexity for each list operation. For example, add element at position j needs to consider 4 cases. The list is empty, adding in front, adding to the end, or adding in the middle. There is also additional space consumption, of course, for storing the previous reference variable for each node. of the list. So here are the complexities of operations for both implementations of the list abstract data type. Getting element by position, it's cheaper in the array, except when we're getting something from the beginning of the list. In this case, it's also cheap for the linked list. To search for an element, for the position of a given element in sequence, takes big O of n time for both implementations, except for the array, we can keep our elements sorted, and in this case, it can be found kind of in time big O of log n. Adding element at position j in generally takes big O of n operations in both cases. Adding at the end of the array can be cheaper and can be done in time big O of 1, except the case when we need to double the capacity. And adding in the beginning and the end of the linked list also is done in constant time. Removing from the end of the array is cheap, big O of 1. Other than that, removing is always taking big O of n operations. And for list, we can remove both from the beginning and the end in time big O of 1, given that we implemented it as a doubly linked list with tail pointer. In Java, we find quite literal implementations of these ideas in two classes called array list and linked list. Now that you know how the internals work for each underlying data structure, which of the Java lists would you use if you often need to get an element at position j? So would you use an array list for that or a linked list? Which would you prefer if you are often adding a new element at the beginning of the list? An array list or a linked list? To test that you understood how it works, go to the top hat and answer a couple of questions of this sort.